like old ghetto one, but it all sounds so much nicer. All right, so Q. We started out with animation, correct, on the calculator, so I'm kind of going to go through it, and I'm not going to go through how we developed the rotation matrix, because that's what you did on your homework. So animation, we have plain language and programming code. Plain language is the description out loud. Programming code is what you type in the calculator. More likely than not, your programs are written in a hybrid. Yes, like on your paper, you write them kind of like a hybrid, like you draw out the matrix and say, so matrix A, instead of writing out the programming code or writing in plain language. We know how to do lines. Lines go from AB to AB points, so there are 4 numbers in the points. Circles, you haven't used much of lately, but you might be using them in your program. Starts out with a point, comma, radius. Yes? If you're making circles in your animation PAL, I would actually steer away from them. If you want to make a circle in your PAL, you're better off doing like a hexagon, because the circles take so long to draw that you kind of lose the effect of your person when their head is taking forever to get on the screen. Okay? So it's, in the short run, it's longer because you're like, 6 lines instead of a circle, but your animation looks better. Loops. Loops help you repeat. So you're doing something 5 times in a row, whatever times in a row. They always start with a 4 and end with an end. Yes, and you do something inside of that you want to repeat. You can do the dummy loop, which leaves it paused on the screen, where you just do the 4 immediately followed by the end. So far, so good. Okay. General animation outline. Make sure you're with me on that one. What do you always do first in an animation program? What's the first thing that you always do, Logan?
Setup program.
Beautiful. After you have your setup program, what do you do, Maddie with a Y? No. Setup program. Oh, Julian, what are you going to right now? Oh, beautiful, because the salmon sheet is very beneficial, huh? So you start with the setup program. I forgot I got to do it here. Ooh, it looks awesome. So you start with the setup program, and then what do you do next, Julian? Perfect. Sometimes you do that like once go A. Sometimes you do that using matrices. So then you would have your setup, you have your initial values. So like here's this matrix. And here's my other matrix. Okay. What do you do after you set your initial values? After you set your initial values, please, Kelby Koo. Perfect. That's a 4. See, from 1 to 7. Going to do something 7 times in this particular case. After you started your loop, what do, Samuel? Wow, you reappeared.
Actually, you draw your things, your lines.
Perfect. So you draw your figure. After you draw your figure, what do you do, Logie Bear?
You change your values.
Perfect. So, for instance, if I'm doing a translation, I'll add my matrices and restore it. After I've changed my values, what do? Maddie with a Y. Delay. Perfect. Remember, that's a 4 and an end. What letter can I not use in my delay?
A or B, or C in this situation.
So D for delay. 1 to 100, and I'm going to immediately end it. After that, what do, Samuel?
Clear draw and end again.
Perfect. And then that's your general animation program. So we use the area of a triangle, 1/2 TU sine theta. We did that so that we could get this sine of a sum formula down the road. Because, remember, we had the big triangle with A plus B. And then we said the area of the big equals the area of each of the littles added together. So we learned this new formula so that we could do the trig identity. Transformation. What is a translation? What does a translation do? Logie Bear. Yep, just like shifts it along. Using matrices, how do I do it? First of all, how do I know what size matrix B has to be? Kelly. How did I know this had to be a 2x2 for my translation matrix? Oh, you're thinking multiplication. I know what you're thinking about now. So, You're thinking the rotation. What has to be true with translating it, Adam? Same dimensions. So your initial points, you need this to be, the translation matrix has to be the same exact size. And then what operation do you use to translate matrices? Maddie with a Y. You're like the popular one today. What operation do you use to translate matrices? What? Logie! What operation do you use to add matrices? You use addition to translate matrices. Good. Moving on. All right. What is a rotation? Kelly! When you rotate an object, what does it do? Turn it. Beautiful. So it turns the object. What is the rotation matrix that we came up with on Friday? What is that rotation matrix? Sam. Good question, right?
Cosine 60, sine 60, negative sine 60, cosine 60.
Okay. What direction does it turn? What direction does it turn? Logie there. Counterclockwise. And how would I get it to turn clockwise, Adam? No. Kelly? Maddie, why?
Use the negative angle.
You got it. Negative angles go clockwise. So you should use a negative angle if you want it to go clockwise. Inverse is not the same. Inverse and negative angles aren't the same.
Can you just change the signs on the signs?
No, you can't. But that's a good question. So you have your rotation matrix to use negative angles to go clockwise. Normally it goes counterclockwise. What operation do you use with your matrices to rotate them? What operation? Row. Add, subtract, multiply, or divide. Yeah. So you multiply your point matrix times your rotation matrix to get your new matrix of points. All right. So then going backwards in time. What's a reflection? What is a reflection? Lila Lou? Yeah, the opposite of the original. It's a flip. A lot of people third block couldn't word it, but they were like doing the hands. They're like, palm, reverse, or like this. That's a reflection. So it's a flip of it. We're going to do them very easily. Like we're going to flip it across the x-axis. We're going to flip it across the y-axis, and you're going to do it without me. That's how easy it is on Thursday. Okay. Then we did a ton of trig identities. Do you see all these trig identities? Yes. And then we're still not overly solid on them. True. Okay. But we're getting there. Why does the cosine of theta equal cosine theta, cosine negative theta? Cosine theta, I'm going to tell you. If theta's here, this is negative theta. I cannot tell you how many wrong pictures I saw on your homework that said, oh, this is negative theta. All angles start at 3 o'clock. Positive angles go up, negative angles go down. So why is the cosine the same? Why is cosine the same? Non-sweaty heavy. Don't worry, we got Kelly. From what axis? No, from the y, but it's the x. So this distance here, this x distance, is the same distance away from the y-axis. Cosine talks about left-right position. You could also look at the graph of a cosine function. The graph starts out like this. These are different theta values. So, for example, if this was negative 30 and this is 30 degrees, do those have the same y value? Yes. Okay. 90 degrees and negative 90, I did it backwards, have the same y value. All right. So the next one you had was the negative sine theta equals sine of negative theta. Let's do that in terms of the Ferris wheel. Here's theta. Here's negative. Why does this equal this? Why is that true, Adam? So we all have to figure that out because on your assessment, you have to explain it to me and report. Jason.
What's your question?
Why is that true?
Why is
Using
negative sine theta equal to sine negative
Yep.
theta? Because if you have the sine theta and then you make it. Oh, it's because like halfway through the sine is 0 at 0.
Yeah.
Because it's like the y value.
I think what he's trying
I
to
don't make any sense in my
he makes no sense, but what I think he's using is the graphic approach, where he's saying, like, imagine this to be 30, this to be negative 30. This one goes up, this one goes down, but is it the same? It's the same y value, opposite directions. And remember, negative means opposite. The same distance, Adam's got it for the other one. Same distance from the x-axis. This y value is the same distance, but they're opposite signs. One's positive, one's negative. Okay? So the next one, these right here, the cosine theta, sine negative theta. There are two approaches that you can use to explain those. One is the graph. That is the graph of cosine. And then this is the graph of sine. What do you notice about those two graphs? Go again. They're shifted. And they're shifted by how many degrees? 90. Hence why they have the same values 90 degrees away from each other. The other rationale is using the same assignment we've done since Sim 1. If this angle is theta, what's the other angle in that right triangle?
90 minus theta.
Okay, 90 minus theta. I didn't use my sticks. 90 minus theta. So the cosine of this would be number 1 over number 2, correct? Okay, the cosine of theta would be number 1 over number 2. Isn't that the same as the sine of this angle? The opposite over adjacent? And you can flip-flop it with a cosine and sine. So those two are equal. Then we developed, and I'm not going through how we developed, the sine of a sum and the cosine of a sum. Today we're going to develop the cosine and the sum of a difference. Okay? And we're going to develop some more of those honors formulas that you've done already. This week we will start getting into 2D projections. And then after vacation we'll go into 3D. And then we'll be near the end of the unit, just putting all the pieces together. So far, so good? Okay. Homework's in your left. And we're going to complete page 330.
So we graduate in July or June?
Page 335. You graduate in July. Page 335. Go.